7.1, we're estimating the mean mu, it's population mean, when our sigma, which is the population standard deviation, is known. So when we go through these, we have a couple assumptions to make. We have a simple random sample of size n drawn from a population of x values. So we're looking at a sample. The value of sigma, the population standard deviation of x, is known. You must know that population standard deviation for this. If the x distribution is normal, then our methods work for any sample size n, as long as they tell you it's a normal distribution. If you don't know it's normal, you must have a sample size of 30 or better. If you don't have that, then you cannot say that we have a normal distribution. We can't use these methods if we don't have that sample size of 30 or better, or they tell us we have a normal distribution. Now going through these, there's a bunch of definitions to kind of know before we can go on. First off, we have a point estimate. A point estimate of a population parameter is an estimate of the parameter using a single number. So x bar, which is our sample mean, is a point estimate for mu, which is our population mean. So that sample is an estimate for then the population. Your margin of error is the absolute value of the difference between the sample point estimate and the true population parameter value. So that's how much difference between your sample number and your actual number. Your confidence level measures the reliability of an estimate. So when we look at confidence levels, we might have like a 50% confidence level, an 80% confidence level, a 95% confidence level. That's how confident or how reliable our estimate's going to be when we find it. Your critical value, your ZC. So for a confidence level C, the critical value ZC is a number such that the area under the standard normal curve between negative ZC and positive ZC equals C. Kind of confusing, but it'll make more sense when we get to our next slides here. So for example 1, it says use the Z table to find a number Z of 0.99 such that 99% of the area under the standard normal curve lies between negative Z.99 and Z.99. That is, find the Z.99 such that the probability of the negative is less than Z is less than the positive of the 0.99 equals your 0.99. Again, a lot of 0.99s here. So you are going back and doing what you did back in Chapter 6. Remember, back in Chapter 6, if we want to figure out what our Z value is, they're giving us the area inside of our graph first. So we have that nice little formula that's the 1 minus A all over 2. So 1 minus our area is 0.99. So if we subtract those and divide by 2, we get 0.005. Again, this is just what we did back in Chapter 6. So now we want to find inside the table, not outside the table, inside your Z table, you want to look for what is the closest number to 0.005. So again, you want the closest number to 0.005, and then you're going to move out on your Z table to figure out the Z value that goes with it. So go to the negative side of the Z table. And right now, search for 0.005 or a number very close to it inside the table. So you should see that Z is going to be very close to about negative 2.58. But when we talk about our ZC, we always use the positive of it. So if we want to find that ZC they're talking about, or our confidence level Z, we're going to have a 2.58. Again, you looked inside the table for 0.005. Then you looked on the outside because you want to find the Z that matches up with it. So it's the negative 2.5, and then the column 0.08. Now, we would have to do this every single time whenever they tell us what the confidence interval is or the confidence level is. However, if you look in that Z table in the bottom left-hand corner, you're going to see this nice little chart. So that's our level of confidence with our confidence value ZC. This means you do not have to constantly look values up in your Z table. You will have them right there in this nice little table for you, and they will tell you what the ZC value is. So they're going to give you what the critical value is for 70%, 75, 80, 85%, and so forth. And all of those are ones we will be using. We will not use anything else besides what's listed in that chart. So you have that chart again in your Z table packet. So I don't know if you need to circle it to remind you. That is what you're looking at. Now going through these, if we know our population standard deviation, to find our maximal margin of error. So the maximum margin of error estimates the difference between the point estimate and the population parameter. This is the biggest gap you can have between that sample mean and our population mean. So our ZC is sigma over square root of n. So you have to first know what the critical value is with your confidence, with your level of confidence. You got to know your sigma or your population standard deviation. You have to know n, the number in your sample. Then we're going to find what we call a confidence interval. Confidence interval for our mean is an interval where C is a proportion of confidence intervals based on random sample sizes of n that actually contain your population mean mu. So what you're going to do is take your sample mean minus the error, sample mean plus the error, and that will give you the range of what the actual population mean is going to fit into at that level percent confidence. So again, we are going through in 7.1 when our sigma is known. So we know the population standard deviation. Now going through it, we have all these requirements. They're the exact same things I've already covered. So just remember, you have to have a sample size of greater than or equal to 30, or they have to tell you it's a normal distribution when you go through it. And then you're going to take x bar minus e and x bar plus e when we go through these. You're doing the same thing every time. Okay, so for example 2, Julie enjoys jogging. She has been jogging over a period of several years, during which time her physical condition has remained constantly good. Usually she jogs 2 miles per day. The standard deviation of her time is 1.80 minutes. During the past year, Julia has recorded her times to run 2 miles. She has a random sample of 90 of these times. For these 90 times, the mean was x bar equals 15.60 minutes. Let mu be the mean jogging time for the entire distribution of Julia's 2-mile running times. Find a 0.95 confidence interval for your population mean. So they're giving us a lot of information here. If it's a 0.95 confidence interval, we want to find the Z of 0.95. So again, go to your Z table, look at that little chart at the bottom. Or again, go back one page in your notes, that chart's in there too. The Z of 0.95 is going to be a 1.96. Now remember, for the rest of our E formula, we need to know what our sigma is, and they tell us that's 1.8. We need to know what our N is. We're looking at 90 times. So our E formula is going to be the ZC sigma over square root of n. So 1.96, and then we're going to have our sigma, so 1.8 over square root 90. So we want to type that into our calculator. It might be easier if you put parentheses around your fraction. So you're going to type in 1.96 parentheses 1.8 divided by square root 90 in your parentheses. and I have 0.37. So I'm going to do about 2 decimal places. WebAssign will tell you again how many decimal places they want. Most of the time, I believe it's 2 or 3. So there is our E, our air. So now we have to plug it into our confidence interval. So we do x bar minus E and x bar plus E. Now in our problem, they tell us the x bar is 15.6. So we're going to get about 15.23 to about 15.97. Now we're not going to stop there. We're going to write a sentence of what this means, because you just saying what these numbers are is not telling me then what is going on in the problem. Because what we're saying is between these two values, the population mean should occur. So we can conclude with 95% confidence that the interval from 15.23 minutes to 15.97 minutes contains the population mean of jogging times for Julia. So again, going through this, we have to state what percent confidence we are, because if that level of confidence changes, that means our interval is going to change. We also have to say what those two numbers mean. We're talking about minutes. I'm not talking about hours. I'm not talking about meters. I'm not talking about yards. It's minutes. And that it contains that population mean for her jogging times, because we are always using these to estimate our population mean times. Now you're going to try the second one. It's going to be very similar to what we just did. So go through, I'll read it with you, and then pause the video and see what you can do on your own. So Walter usually meets Julia at the track. He prefers to jog 3 miles. From long experience, he knows that sigma equals 2.40 minutes for his jogging times. For a random sample of 90 jogging sessions, the mean time was x bar equals 22.50 minutes. Let mu be the mean jogging time for the entire distribution of Walter's 3-mile running times over the past several years. Find 0.99 confidence interval for mu. So again, pause the video, see what you can do on your own, and then come back with me. Okay, so we're going to set this up just like we did our other ones. Now, for example 2 and for this you try to, they are using 90 for your n. Because we have a number that's bigger than 30, it doesn't matter if we have that normal distribution, because we can go back through and use our ZC and our E formulas, because that n is bigger than 30. So as long as that number is bigger than 30, you don't have to worry about anything. It's when it's smaller than 30, they have to tell you something about how it's a normal distribution. So your Z of 0.99, you used your chart. So if I look at that, we should have a 2.58. Tells us our sigma is 2.4, and our n is going to be 90 again. So I take my ZC sigma over square root of n. So we've got 2.58, 2.4, square root 90. So again, that should have been how you started. and you then get an E of about 0.65. Now make sure you are actually typing these into your calculator and we are getting similar numbers, because I want to make sure you can type these in, because you have to be able to do that on your tests and quizzes on your own. Okay, so x bar minus our E, x bar plus our E. So my x bar here is 22.5 minus 0.65. 22.5 plus 0.65. So about 21.85 to about 23.15. So your number should be very close to mine. So we can conclude with 99% confidence that the interval from 21.85 minutes to 23.15 minutes contains the population mean of jogging times for Walter. Again, we are doing just about the same thing every time as you go through these. So the only hard part is remembering your formulas that you have to have. Remember, you can write any formulas down you want on your note cards for your tests. Now you can put this into your calculator. I don't use this much at all, but I will show you how to do it. However, you cannot find your E using this Z interval. You have to use the formula to find your E. So as a heads up, you might find your interval, but you still have to go through and figure out what your E is using the formula. So if I want to use my calculator, we're going to look at the last example you just did on your own with Walter. We're going to use the exact same numbers with the Walter problem. So we would hit our stat button, it says. We're going to go over to tests. Now you're looking for Z interval. So we want to scroll down to Z interval. Now going through this, you can choose data, you can use stats. We're going to leave it on stats because sometimes if you type stuff into your calculator, it will have all of those recorded there for you. It will tell you what your sigma, x bar, n is, depending on what you've already typed into your calculator, into your L1 or L2, anything like that. So I'm going to leave it on stats, change it as we're going. Now in our problem, it told us our sigma was 2.4. It told us our x bar in this problem was 22.5. And we had 90 jogging times. And then our confidence level was a 0.99, so 0.99. We're going to go down to calculate. Now here it tells you what your interval is going to be very close to. So it's saying about 21.848 and 23.152. Now if you look at those numbers and our numbers, it's the same. It's just they rounded 3 decimal places, not 2. So you do get the same interval. It's a nice way to check yourself. But they do not tell you what your E is. You're going to have to do that by hand. Now the last part of this section then is going to be working backwards. So they're going to give you information, and they want you to solve for n. So they are asking you, what is your sample size? So they are going to give you what the confidence level is. They're going to give you your standard deviation, and they're going to give you your E. So they're going to tell you what your error is. Now, as you go through these, you're finding a sample size. So if I am talking about the number of people and you find that n is equal to 10.3, we can't have 10.3 people. We're going to always go up to the next number. So if I have 10.3, you're bumping it up to 11 then. So you cannot leave your n as a decimal because we want to round to the next whole number because we're talking about objects. And you can't have half of it or part of an object. Okay, a wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. A preliminary study shows that sigma is 2.15 pounds. How large of a sample should be taken to be 99% confident that the sample mean x bar is within 0.2 pound of the true mean weight mu? So it tells us 99% there, so we have to figure out what our z of 0.99 is. Again, go to your little table on your z table, and that's going to be a 2.58. Then we have to know what our sigma is, and they tell us that's 2.15, and we got to know what E is. Now, they don't really come out and say what E is, but they're saying they want it within 0.20 pounds. So they're saying your E is 0.2 because we're going to be within that amount. That's your error. So I'm just following the formula. Okay, so we have to then do 2.58 times 2.15 all over 0.2 squared. So you're going to type that into your calculator. Be careful as you're doing that. So when we go through it, we get about 769.2. But remember, we can't take a decimal. We are talking about finding the number of salmon. So we have to have then 770 salmon. Because again, you cannot have point of something. So you have to round up to the next if you're trying to figure out how many should be in your sample. Again, if you have questions, make sure you're going through, looking at the web assign help too. Send me questions if you got them over these. Make sure you're typing it into your calculator correctly. That's going to be probably the biggest thing. Because if you type it incorrectly, then it will give you the correct E value. But if you do it out of order or anything, it's going to give you different E values, which will change your answers then for you.